Our next speaker is actually a new researcher. It's not you. It's Bing Chat. And Bing Chat will be talking about researching the researcher. Now, I'm just kidding. It's not Avon. It's by design. Seriously, with our next speaker, our next talk today is on exploring the Windows registry as a powerful LPE attack surface. Our speaker today is Mateusz Jurczyk. Jurczyk. Thank you. I hope you all enjoy. After this, again, Q&A session, 3:15. It's going to be in the village, specifically the MSRC village. All right, thanks, y'all.
Hi, can you hear me? Hello, I am Mateusz Jurczyk. I am a security researcher in the Google Project Zero team. And I've been doing low-level security research for a while. And here today I would like to talk about my latest research project, which is on the Windows registry and how it can be used to achieve local privilege escalation in the Windows system. So welcome. I have many slides, so I will power through the first few of them. So this is the registry. You probably all know it through the registry editor, which is the standard tool in Windows to fiddle with system settings. That's been there for quite a while. Windows XP, because it's the best system. I love the aesthetics. Also, it was the first system in which I actually did anything meaningful with the registry. But what you may not know is that the registry is like a huge piece of code in the Windows kernel. So actually, it was introduced 30 years ago in Windows NT 3.1, around 30 years ago. And it started as a relatively simple piece of code, relatively simple functionality. But over the next 30 years, it has actually grown around tenfold. This graph is created based on decompiled code that I took the kernel from every major version of Windows, decompiled it, and counted the number of lines of code handling the registry. And it only counts the kernel part of the registry because there is also a big part of registry implementation in the user space, but that's not as relevant to security. The growth seemed kind of linear, but from a security perspective, there are actually 4 operating systems that introduced the bulk of the interesting changes. So it was originally Windows NT 3.1 with the original implementation, and then Windows XP, Vista, and Windows 10 16.07, where the biggest changes were introduced. And it's like 3 different types of changes in Windows. So first of all, it's basically optimizations to make the registry run more fast. Then we have things like legacy mechanisms, for example, the registry virtualization introduced in Windows Vista. And then we have some new features which aren't really user-facing, but are there, for example, for software developers, such as the introduction of transactions or container support. So you might be asking, why would we want to attack the registry in the first place? So as the title of the talk says, it's a local attack surface that when you actually find and exploit the bug in the registry implementation, it allows you for going from user to kernel privileges most of the time. And it's very interesting because of the fact that it's very close to very sensitive data in the system, right? So the registry, as you probably know, stores information such as system configuration, user credentials, and so on and so forth. So first of all, you may have standard issues that are typical to any C code, such as memory corruption. But then you also have logic bugs and information disclosure, which, thanks to the fact that the registry handles such sensitive data, also have a very high security impact. And you also have interesting classes of bugs where the registry isn't attacked as itself, but it can be used as a medium to attack other highly privileged processes in the system. And a very low-level reason for attacking the registry is that, as I showed you, it's a huge code base that consists of both old and new code, right? So it's a very interesting mixture of code from 30 years ago mixed together with code from, let's say, last month. And it's like layers and layers of complex mechanisms that have to interact with each other. So from a security perspective, this is like a dream come true from someone that wants to find bugs. I will just quickly go over this. So when it comes to publicly known security research, there isn't that many compared to how interesting I think the registry is. So I think there is a lot of work being done internally at Microsoft, considering the number of changes that go into the registry over the years. But when it comes to the public space, I haven't really seen that much. So I know that I have done a little bit of research in the past. A few of my peers as well, for example, James Forshaw has been very prolific in finding logic issues in the registry throughout the years. And there are some other isolated cases documented on the web by other authors, but really not too many of them. So when it comes to this effort, it all started in May 2022, so it's over 1.5 years from now. And back then, I didn't really want to make this such a big research target for me. I just wanted to test my new coverage-based fuzzer for the Windows kernel. And registry hives were one binary format that I could easily plug into the fuzzer. So as a result of that, I found one bug which was related to incorrectly formatted security descriptors, which makes sense. But it was just a single bug, right? So it can be, you can view it as a success story or a failure story. But for me, mostly it was a reason to start digging into the code of the registry and figure out exactly the root cause of the vulnerability, see if there were any variants, and see exactly what was going on, right? And so I got so hooked into looking at the registry code that I started, analyzing it further. And at some point, it basically ended up as a challenge to review all of it because it was so interesting. So that's what I've been doing for the last, 17 months or something. And I would like to show you the research process that I followed for the last 1.5 years. So first of all, I would try to pick a small part of the registry that is relatively self-contained and try to reverse engineer it in IDA Pro and Hexrise, trying to get it as close to readable C code as possible. Of course, I don't have access to the source code, but we can get pretty close to that. Then once I had that, I would try to understand the logic of the code. What exactly is it trying to do? What problem is it solving? How exactly is it doing so? And if there are any internal consistency problems with the code. Then knowing how the feature works internally, I would try to compare it with everything that I had previously learned about the registry and think if there are any kind of problems with interactions between these features and other features in the registry. And finally, I would basically go and test, reproduce the bugs that would turn out to be real based on all of the ideas that I have accumulated earlier in the process. And I would try to, write good bug reports and report it to Microsoft. So of course, this is a very simplified view of the process. It's never as simple as that, but that's the basic framework. And I would basically repeat this process many times for each of the major features of the registry. So first of all, I would start with the hive loading part, which is the most easy to start with, I guess, because it just does kind of binary parsing and binary format sanitization. Then I would move on to basic operations that you know from regedit, such as creating keys, setting values, and so on and so forth. And I would then move on to things like registry virtualization, transactions, differencing hives, registry callbacks, and so on and so forth. So that was my basic process. And when it comes to the results as of last month, now, first of all, I would like to note that it's really hard to actually quantify what a bug really is because of the fact that, in many cases, either I reported one bug and it would be fixed by multiple changes in the code, or the opposite situation where I would report several bugs and it would be fixed by just one code change, right? So it's really hard to say what exactly a bug is and what exactly a fix is. But when it comes to the hard numbers, I filed 33 issues in the Project Zero Bug Tracker, which is our main way of reporting bugs. That, in my opinion, corresponded to around 45 unique problems, but that's highly subjective. These 33 issues were assigned 39 CVEs by Microsoft, and out of them, 33 were the most severe elevation of privilege, and 6 of them were some kind of information or memory disclosure. So all of these bugs are basically documented in the Project Zero Bug Tracker. So here is a list of all of them as of last month, and all of them pretty much are very interesting. I had a lot of fun writing every report. So if any of the bugs that I will be talking about today pique your interest, then you can just go to the Project Zero Bug Tracker, read the report, download the proof of concept, and play with the bug. So now let's talk a little bit about the process, starting with reverse engineering. So basically, it was an essential step. It probably took around 70–80% of the total research time, so most of it. Primarily, I was analyzing Windows Server 2019 because of the fact that that's what I was using for the fuzzing. So I created this environment in IDA Pro, and then I didn't really want to move on to another version of the system. So I just kept analyzing that one, and then for every bug that I would find, I would try to reproduce it on the latest Windows 11. As I said before, I mostly used IDA-Pro together with the Hextrace decompiler for that purpose. And what was really very, very helpful for me were the public symbols that are made available by Microsoft for the anti-OS kernel. So that gives you function names, global variable names, structure layouts, some of them, and some of enum definitions, which is already a lot if you want to reverse engineer such a huge code base. So I want to give you an example. So this is a function called cmget-kcb cache security, which is a relatively small function. And here is what happens when you load it in IDA-Pro together with the symbols, right? That's the starting point without doing any actual manual reverse engineering. So it already gives you a little bit of information. So you see that the function has a name assigned to it, and also the other functions that are called by it are also named. But otherwise, it doesn't really look so good, right? So the names of the parameters, the names of the local variables are ambiguous. The types of the variables are all set to int64, which doesn't make much sense. You have some direct references to some offsets in some structures, but you don't really know what exactly they mean, and so on and so forth. So really, you can kind of read this code, but it's really hard to reason about it and find any bugs by just looking at it, right? So here's what happens after, like, I don't know, maybe 3 or 5 minutes of work as a reverse engineer, once you already know a little bit about the registry. So here you can see that you have very pretty local variable names. You have all of the type information, the structure pointers assigned to the variables. And this is actually, I think, very close to probably to the original source code. You know, the constant name is changed to its corresponding name in the enum. So having something like this, you can actually start thinking on a high level about the code that you're looking at and start to look for some logic issues, for example. And then I basically repeated this process for 100,000 lines of code, more or less, I guess. So, you know, a lot of this process is actually kind of mechanical. You don't have to think too much about it. You just click and use the IDA shortcuts and whatnot. But there is also a hard part about it. First of all, you have to deal with some compiler optimizations. So it's not always very clear code. Sometimes you have inline functions, mangled arithmetic, and stuff like that. And the hardest part of all is basically, as in every reverse engineering process, it's to figure out the missing pieces, right? So first of all, as I mentioned before, not all of the structures internally, the internal structures in the Windows kernel are present in the public symbols, so you have to really reconstruct your layout from scratch based on the information that you have. And the same goes to enums and flags, which is really, really hard to do, and you really have to guess a lot to figure out what they possibly can mean. So my request being here at Microsoft is to publish more information through the public symbols, because it really saves security researchers a lot of trouble, a lot of manual labor that could be better spent actually looking for vulnerabilities instead of going through this reverse engineering process. So then let's move on to understanding the code. I think that's the most interesting part of this whole process. So once we have the code that is readable and we can reason about it, there are many questions that we can ask that can kind of lead us to vulnerabilities, right? As I mentioned before, what problem is it trying to solve? Is it exactly written in the same way that I would personally write it? And that can help you figure out if there is something wrong with the code or if there is something wrong with my own understanding. You know, and then is it internally consistent? Does it handle error conditions? Does it behave in the same way that it's documented? And so on and so forth. So there is really a lot of questions to ask here. And it's very cool, this part of the process, because it can expose very, very deep logic issues. And also not bugs by themselves, but kind of structural weaknesses that you can then generalize on the whole code base. So today I would like to give you 3 examples of some deep-rooted bug classes that are specific to the registry. So first of all, there is resource exhaustion, which is potentially a big problem in the registry. Somewhat related to that is the handling of partial success in multi-step operations. And then another kind of class of bugs are the constraints of the Hive binary format, expectations versus reality. So let's start with the first one, resource exhaustion. So, you know, if you want to do any operation in the registry that creates some object or sets some object, such as creating a key or setting a value, the code responsible for that operation has to allocate some memory, obviously, to store that information somewhere, either in the Hive itself or the kernel pools, or very often both. And a local attacker has a lot of influence over this process, so they can actually try to interfere with these allocation requests by exhausting both types of memory. First of all, Hive storage, which is very practical for a local attacker to actually exhaust, and also the kernel pools as well, which is slightly less practical because of the fact that normally you have more memory that you can use for kernel pools, and if you exhaust all of the kernel pool memory and the system is out of memory, then if the kernel cannot allocate a few kilobytes of memory from the kernel pool, it may crash somewhere else before we can even reach the code that we want to target for the vulnerability. So let's talk a little bit about the Hive size limit exhaustion. So, there are actually two types of separate quotas enforced on the registry size in Windows. So first of all, by design, the maximum size of every single Hive in Windows is 4 gigabytes, and that is kind of non-extendable because of the fact that cell indexes which are used to address data within registry Hives are like 32-bit unsigned integers, so they can only address 4 gigabytes. And then also we have this other limit, which is the cumulative system-wide registry quota, which is currently also set to 4 gigabytes. So first of all, every registry Hive can be a maximum of 4 gigabytes, but also the cumulative size of all of the registry Hives is also capped at 4 gigabytes. So we have two very good, reliable ways to actually cause the internal HV allocate cell function to fail as a local attacker. And this really opens up a plethora of interesting error code paths that we can review, right? Because every such failed allocation has to be gracefully handled, and the state of the registry has to be restored to a consistent state. And the other interesting fact is that most of them are probably very poorly tested because of the fact that these resource exhaustion conditions don't really happen in production systems, I think, all that often. So then there can be even trivial bugs in such error paths that just may have possibly never triggered on a real system. So that's something for us to look for. And this was basically one of my main focuses throughout the research. And a very good starting point is basically to take an allocation function, such as on the left we have the HV allocate cell and all of the 30 references to it. So this is kind of a manageable amount of call sites that we can just go one by one and see what happens if any of those allocations fail and if their conditions are handled correctly. And there are many more references to pool allocation functions. Here is just one example of the CMP allocate pool function, but there are also a lot of calls directly into X allocate pool with tag at other internal functions. So when it comes to pool allocations, there is much more of them. Then we have the multi-step operations, right? So, as I have just shown, handling errors within the scope of a single function can be hard and problematic, but it gets even harder if you want to do proper error handling across function boundaries, right? Because in the Windows kernel, you have the anti-status return type, which is used to pass information about errors and, the status of a function. And in theory, it carries some, relatively a lot of information because it's a 32-bit type. But in practice, it's mostly used as a Boolean differentiator between a success and a failure. So it isn't really used to capture information about the overall status of the operation, but mostly just what was the last error that was encountered. So admittedly, there aren't that many functions in the Windows kernel that do this kind of multi-step operations, but there are still a few of them to look out for. For example, in the case of registry, related to the registry virtualization mechanism or related to transactions. Here, unfortunately, I don't have too much time to go into the detail of those bugs, but they are very interesting. So here's a list of some of them that were related to either error handling or the handling of the failure of multi-step operations. So you are very welcome to have a look at any of them because I think they are very interesting. And then we have the constraints of the Hive format, right? So when a user is loading a Hive in the system, the kernel tries to actually check first if all of the internal structures inside of the registry Hive are consistent, so we just don't load a corrupted Hive that will break something in the future. So we have a whole family of internal functions starting with the CMP check something prefix, which do all of the checking of the keynodes and value lists and all of those internal structures. And these are quite strict and generally quite well written, but it's important to note that they still are more permissive when it comes to the types of structures that they allow. compared to what the kernel would organically produce on output, right? So the set of states that you can load in the Hive is still bigger than the sets of states that would be normally produced by Windows, which is something to keep in mind, because if at any point the kernel code assumes that these two sets are equal, then there can be a potential for security bugs. So here are some examples of some very odd constructs in the registry Hive that don't make any sense in general, but they are still accepted by the loader, even though they would never actually be produced by the kernel, right? It's not an exhaustive list. You would probably find many more examples, but it's a list of some of them. And again, unfortunately, I cannot do a full case study, but at least 3 of these actual weird states led to actual like severe buffer overflows or use after freeze, because the kernel code didn't expect any of these nonsensical structures to ever exist in a Hive, but they were actually allowed to be loaded by the loader. Right. So once I actually thought I found all of the bugs that I could find inside of a specific feature, I would try to think about how it can interact with other parts of the registry. And this is also a very interesting part as well, right? So I have to start off by saying that I really like the original design of the Windows registry from Windows NT, because it did exactly what it advertised, right? You had some operation like creating a key, you could call it, and then it would behave exactly as you would assume it does. But then we got these increasingly complex features that were being introduced in newer and newer versions of Windows, which started complicating the internal state a lot. And every such new feature basically adds some kind of magic that is non-intuitive. First of all, it can be non-intuitive for the user mode application that is using the registry, but also it can be non-intuitive to existing parts of the registry implementation in the kernel. So I would like to consider and talk a little bit about how these special features deviate from the baseline mental model of the registry, right? So first of all, we have special types of keys, right? We have symbolic links, which you may know from other parts of the operating system, such as the file system. So instead of having a normal keys with values and so on, we have a key that just points somewhere else. So when we open it, this key is not really open, but some other key at some other arbitrary registry path is opened instead, right? So this is first a very non-intuitive behavior that has been used in a lot of attacks in the past. And then we have this even weirder type of key, which is a predefined handle key, which is kind of similar to symbolic links, but instead of pointing to an arbitrary path in the registry, it points to an arbitrarily chosen predefined key, which means one of the top-level keys, such as HKLM, HKCU, and so on and so forth, right? So in order to store the information about where this key actually points, the value list part of the key node was reused for that purpose. So that means that the key actually doesn't have any values. And because of this super rich semantics, it cannot be operated on by any syscalls in the system other than the open syscall, which allows you to actually figure out where this key is pointing. Then you have registry virtualization, which is a compatibility mechanism introduced in Windows Vista, which creates the illusion of running as administrator. So you can imagine that you have some old application that always thinks that it's running as administrator and thinks that it can write to HKLM software, for example, which is a global system Hive. So in order to keep this application running, what Windows Vista does is that it silently redirects all reads and writes to HKLM software to another user accessible registry key under HKCU, which is again quite non-intuitive, because the outcome is that first of all, you may be thinking as an application that you're creating a key in one place and you're actually creating it somewhere else. And similarly, you may be, for example, enumerating values or reading values, thinking that you are doing it from a key within HKLM software, and you're actually reading from 2 different places because the registry silently merges the state from HKLM software and the corresponding key inside of the virtual store. Then you have transactions, which again make everything more complex, right? So in normal registry, everything is kind of simple. Everything either is or isn't. So we have a key that doesn't exist. You send a request or you call a system call to create the key, and now the key exists. But with transactions, we have more states. So everything is, isn't, or is pending in this case. So we have a key that doesn't exist. We create it transactionally. Now it exists in a transaction, but not in the global view. and then we can decide if we want to commit the transaction and make the key actually visible in the global view, or revert the transaction and then it doesn't exist anywhere again. So this means that basically with the support of transaction, there is basically no ground truth about the state of the registry, because we cannot ask a question about some state of the registry. We always have to add information, like in the context of which transaction are we asking this question, right? Because we may have a key that exists in the global view but doesn't exist in a transaction, and vice versa. And every part of a key may be subject to this alternate state, right? So this adds significant complexity to the registry code, because first of all, a lot of code had to be added to implement the transacted operations, but also all of the non-transacted code in registry has also needs to be aware of transactions, because, for example, when you have a non-transacted write operation, then before proceeding with the operation, the handler first has to revert all of the transactions concerning the key before it can actually, perform the operation. And lastly, we have something called differencing hives, which was added in Windows 10 1607. It's another huge complication. So when you have a normal hive, it's just a standalone self-sufficient database that stores some data. But a delta hive, which is another name for differencing hive, is not standalone. It's kind of a patch set that you have to apply on top of another hive that is either a base hive or a delta hive. And when you have nested containers, these delta hives can also be stacked on top of each other. And then when you consider a specific key referencing it through a differencing hive, then it's called a layered key. So here we have an example, right? We have a normal registry tree, which has the root key, and then it has some kind of key structure underneath it. But with differencing hives, we have a tree of trees, right? So we have a base hive at the bottom of it, which is the host view of the registry hive, and then we have upper layers that are overlaid on top of it that represent the changes from that container's view relative to the host view of the registry hive, right? And then if we pick a single key out of each of these hives, then each of these keys has like one of 5 different semantics that are like specific to differencing hives. They are shown here. That basically tell you how you should treat this registry key. And then if you want to think about one specific key starting from a specific layer height, you don't only operate on that key node, you take the key node at the specific layer height and all of the key nodes below it. So to summarize layered keys, I think that they turn everything that we know about the registry upside down, more or less, because every key node now is not part of a single tree, but it's part of 2 trees in 2 different dimensions, which is super hard to even think or reason about. A key is no longer represented by a single key node. As I said, it's now a whole stack of key nodes. And you have kind of absurd situations where the existence of a key doesn't really mean that it exists, because you have keys that are tombstones, which represents the lack of a key. And similarly, the absence of a key node also mean that it necessarily doesn't exist, because you have keys with the merge unbucked semantics. So it all gets very, very complicated and hard to think about. So now the question is, how of all these features work together? And as you can imagine, they don't. This is the situation in the registry. Again, I will just show you a list of the cross-feature bugs that were caused by kind of some problems in the interactions between those features. You can look them up in the Project Zero bug tracker. But I want to show you one case study where something went wrong with the interactions. So we have these weird keys called predefined keys, right? And as I said before, they are supposed to be rejected by almost all system calls, because if a predefined key manages to be passed to some internal kernel registry function that is unaware of their semantics, something bad will happen, a crash or even something worse, right? So for that reason, it's very necessary for all of the top-level system call handlers to actually filter out the predefined keys very early during the execution so that they don't reach the deeper functions. So there is one function that is kind of responsible for facilitating this. It's called CMOB reference object by handle, and what it does is that it translates a handle passed from user mode into the kernel virtual address of that object, but what it also does is that it checks whether the key is not a predefined key. If it is, then an error is returned, and that error is propagated to the system call handler and to user space. So as you can imagine, this is already a potential for bugs, because we have to ask if this single safe wrapper really is sufficient for all of the potential scenarios in which predefined keys can occur. And again, the answer is no, right? So in September 2022, I found the first bug related to predefined keys, which is caused by the fact that we have this special system called NT-notify change multiple keys. And it didn't go through the safe wrapper because of the fact that a different method of referencing a key was used. Instead of just taking a handle to it, an object attributes structure was used to reference the registry key. So for that reason, the predefined handle key was not detected, and it could reach some internal function and cause a security vulnerability. So that bug was fixed by basically introducing a second safe wrapper, which can now not only take a handle to a registry key, but is also able to handle an object attribute structure and also check if the specific key is a predefined key or not. Then next month, in October 2022, I found that registry virtualization also does a similar thing and also doesn't go through the safe wrapper. Instead, it also references a registry key through object attributes. So again, it was fixed by Microsoft by calling into this second safe wrapper that was introduced for a second vulnerability. And then in the same month, I again found that also related to registry virtualization, there is an unsafe function called CMP rebuild KCB cache, which basically doesn't kind of ignores predefined keys when refreshing the security cache after performing the key replication process. So that was fixed again by Microsoft by manually refreshing the security cache when the security of a key was changed. And then in April 2023, half a year ago, I discovered that, when looking at layered keys, I discovered that the safe wrappers that are supposed to actually filter out all of the predefined keys is actually insufficient, because what they do is they only check if the top level key in the key stack is not a predefined key. But you can have a predefined key, or you could have a predefined key somewhere lower in the stack, and that would get accepted. But when you have an operation such as enumerating values, they operate on all of the layers in the key stack, and they would still crash when they would encounter the predefined key that you managed to smuggle in. And then in May 2023, I also found another problem, which was the fact that the CM delete layered key function would also, in essence, would also bypass the safe wrapper and perform like a low-level operation to delete a key in the registry without checking if it's a predefined key or not. So again, it was a use after free because of that reason. So the ultimate fix for the last two bugs was that in July 2023, Microsoft actually deprecated predefined keys completely, which I think is great news, because according to my knowledge, that they are not used almost anywhere, and as you could see, they were the cause of a lot of confusion and a lot of potential bugs, because there are so many places in the registry implementation where you have to be aware of their existence, and you have to be conscious to filter them out, but of course it's very hard to do. And then we have the last part of testing, reproducing, and reporting. So here you can see the life of a security researcher, right? When you do bug hunting, so you are reading the code, you think you have spotted a bug, but then you read a little bit more, you think that it's not really a bug, then maybe it's a bug again. You start testing. Unfortunately, testing is responsible for most of the negative emotions here, because you think maybe you have a bug, and then it turns out that it's not reachable, for example. But what is also specific to registry in this case is that 3 months can pass, you learn about some other mechanisms in the registry, and you figure out that it's actually a real vulnerability, but only when combined with some 2 other mechanisms, right? But what I want to say is that the testing is very important, because given how complex it is, it's actually the only possible way to learn how it works and to validate your understanding of it. So in terms of tooling, I obviously used virtual machines plus Windbag, and there is a great bang reg extension to Windbag that lets you introspect the internal structures that describe registry structures. Also, I use the standard tools such as regedit, process monitor, process explorer, and for some of the more advanced things that there aren't tools available on the internet, I developed my own. For example, for creating symbolic links, loading different sync hives, and so on and so forth. In terms of reproducing the bugs, I always try to trigger a system bug check or like an obvious security violation for every bug before reporting it to Microsoft, so that it's kind of obvious that there is a bug and it's easy to reliably reproduce, which is a little bit hard in some cases, because what is also specific to the registry is that even if you manage to create some inconsistent state in the registry, crashes don't typically just happen as a result, so you have to be very deliberate to actually call some system call or perform some action that exposes the fact that there is an inconsistent state. Thanks to the fact that the registry API is so well documented on MSDN, actually writing the C++ of the reproducers were pretty smooth for me. But what was most problematic, especially in the beginning of the research, was when I had to actually craft kind of semi-well formatted, but with unusually formatted hives that would trigger some condition in the Windows registry implementation, right? Because there is basically no tooling available for that, at least in the public space. Maybe there is in Microsoft. So what I eventually ended up doing was just taking the offreg.dll file, which is an offline registry library that you can use to kind of create registry hives offline without going through the Windows kernel. I took that library and I binary patched it for it to produce the kind of structures that I needed for the proof of concepts. And then, of course, the last part is reporting to Microsoft. So I filed all of the bugs that I thought had any kind of security impact to Microsoft through the Project Zero bug tracker, and then emailed to MSRC. All of them so far have been successfully fixed within our 90-day deadline. Working with MSRC has been great. And the average time to fix for all of these registry cases was 81 days. And the last kind of optional step in the whole process is verifying fixes, which I would encourage everyone to actually do, because there is a lot to learn from it, right? So if you are just doing static analysis based on one specific snapshot in time, okay, you know how the registry works at that point in time, but it's actually cool to actually see how the registry is evolving, how the fixes actually work. It gives you some insight into what the software developers on the other side are thinking as well. So I found this exercise very, very interesting, and I try to go through every Patch Tuesday and bin diff the changes and document for myself what exactly they do. So I think Patch Tuesday was yesterday, so I have some work to do. And it's also a very good way to learn about things that are not related maybe just to fixing the bugs, but also general restructuring, refactoring of the code, some mitigations that may be added, and so on and so forth. So I actually learned about some very nice efforts from Microsoft this way. And then we're surprisingly on time, I think. So there is also a bonus section of exploitation, right? So far I have only talked about how you can find the bugs, and every one of my reports actually contained like a bug check report from Windbag. But the question is it exploitable? And how do you actually get from the crash to elevating privileges in the system using these registry bugs? So first of all, because of the fact that registry is such a huge subject, exploitation of registry is also a huge subject. I could probably do a whole talk just on the exploitation part. But basically, of course, it depends largely on the type of bug that you want to exploit, the initial primitives that you have, and the initial context from which you are exploiting, such as local user or a specific sandbox, and so on and so forth. So of course, the best bugs to exploit are logic issues in registry. They are the most reliable and generally the best, but I didn't really find that many of them, and I think my peer, James from Project Zero, may have something to do with that. Then you have the pool-based memory corruption. Here I also don't have that much to say, because in these cases where you have like a buffer overflow on the pool, you just use the standard state-of-the-art exploitation techniques. But the most interesting in all of these is the hive-based memory corruption, which is a very interesting type of memory corruption specific to registry that is kind of unexplored and gives you a lot of interesting options. And I found a lot of bugs that were actually corrupting memory, not inside of the pool, but inside of the registry hive itself, as it's loaded in memory by the operating system. So just a few quick slides about the exploitation. First of all, let's talk a bit about the registry hive layout. So this is a reformatted picture from the Windows internals book. And it shows you that in Registry Hive, you have a base block, which is a 4 kilobyte chunk of memory or chunk of data that gives you some basic metadata about the Registry Hive, and then the rest of the Hive is formatted into bins, and then these bins consist of something called cell, which is like the smallest unit of data that can be either marked as allocated or free. So that's basically how Registry Hive layout looks like. And so we can compare it to the allocators that we know from user space and from kernel space, such as the heap and pool allocators. There are some similarities. So first of all, we have these free and allocated cells, these chunks of data, which can have arbitrary size and arbitrary data. And some cells, depending on the meaning of the cell, some of them can have a predefined structure, for example, a keynote, and some of them can contain fully controlled data, for example, the data of a value in the registry. But we have also very big differences as well. So first of all, normally when you think about an allocator, it only operates on memory. And in this case, the same data layout is basically maintained all the time, both on disk and in memory. So related to that is the fact that there is no randomization. Everything is 100% deterministic, which is of course great for exploitation, and there are no protections against temporal or spatial violations, which is to say buffer overflows or use after freeze. And further, most bugs which allow you to perform some kind of corruption in the Registry Hive can be in some way transformed into a primitive where you can reliably replace or corrupt an arbitrary object in the Hive. So now, knowing all this, the question is, if we have a vulnerability that allows you to corrupt something in the Hive, what do we actually corrupt, right? Because at first glance, if we think about the type of data that is stored in the Registry Hive, it's all kind of internal and self-contained. So there are no virtual memory pointers or anything that would allow us to go outside of the Hive and corrupt something in the kernel memory, right? And the solution from the exploitation perspective to that are cell indexes. So cell indexes, as I said before, are 32-bit unsigned integers used to reference cells between each other. On disk, they have a very simple meaning, which is basically the offset of the cell in the Hive file, but in memory, it's actually much more complicated to translate the specific cell index into a virtual address, because a Registry Hive is not mapped as a single big blob of memory in the kernel space. Instead of it, it's mapped in the bins that I mentioned before. So when you want to translate a cell index into a virtual address, you have to go through this special kind of structure called cell map, which is very similar to a page table-like structure that we know from, for example, the x86 architecture. And internally at runtime in Windows, there is a special function called hvp get cell page, which takes the cell index. It also takes a pointer to the Hive, which is not shown here. And what it returns is the virtual address where the cell is mapped, and then it can be operated on from that point. So this is another picture from Windows internals, which shows you the structure of the cell map. So you can see here that it's very similar to a page table where it has several kind of layers that are used to translate the cell index into a virtual address. And the trick here that we can use for successful exploitation is that because of how cell maps are currently allocated and because of some specific optimizations that are there in place, we can abuse cell indexes with an out-of-bounds cell index that is larger than the size of the actual Hive to which it refers to get very interesting primitives. So we can get an out-of-bounds cell index to get it to point to an arbitrary address, or we can get it to point to a specific object in memory that exists, or we can even get it to point to itself, which is kind of like a construct like a self-referential cell index. So I wouldn't say it's necessarily like Turing complete, but I think it's like firmly in the category of a weird machine. So in summary, this kind of primitive basically gives you all of the tools that you need as an exploit writer, right? So first of all, you get an address leak from that, and you get also an arbitrary read and write primitive, all with a single bug of corrupting some memory in the hive currently. So it enables a very reliable exploit. Of course, you have to use some offsets and so on, but basically once you have the system configuration and you know what system you're exploiting, you can have like 100% reliable data-only LPE attack. So as an exercise, what I did somewhere at the beginning of the research was actually try to write an exploit like that, and I succeeded after a few days of trying. So this is an exploit for like one of the first bugs that I found, which was an integer overflow in the reference counters of security descriptors, which resulted in a use after free in the registry hive data. And I was able to leverage that to get the leak and arbitrary read and write. So as you can see, what I was doing here was first leaking the base address of the kernel, then iterating the list of processes in the system to find the system process, find the security token of the system process, replace the security token of our own process with that one, and that spawn a shell that run with the anti-authority system privileges, which is a full compromise of the system. So when it comes to the takeaways, first of all, I would just like to say that I think registry is fascinating, as evidenced by the fact, how much time I spent on it in the last months, but it's also very underexplored. So I would encourage other security researchers to have a look at it, because it's very interesting. I think another takeaway, if you're a security researcher, is that deep persistent analysis pays off. So you can find really interesting bugs and the deep bugs and reliable bugs by spending the time to understand the subject very deeply and not only go for the low-hanging fruit, but actually for the more deeper stuff. And if you're a software vendor, then I think there are, of course, fixing particular bugs helps a lot, but there are also some things that can have even more impact, such as attack surface reduction, elimination of entire bug classes, and well-placed mitigations. And I think there is room for all of these things in the registry. Some of them have actually been introduced. For example, the predefined keys have thankfully been deprecated now, which counts as very good attack surface reduction. And I hope that there will be more examples of that in the registry and some successful collaboration in that regard. So that's all I have today. Thank you very much for listening.